Students, can you hear me?
Yes, ma'am.
Yes, ma'am.
One minute. So I think I have completed your fault calculation in your section. So let us start the economic load dispatch. So just I am logging out and then again joining. I have some problem, so I am doing that one. Can you see the screen?
Yes, ma'am.
Okay, today I shall start the economic load dispatch. Okay, economic operation of power generating units. I think it is written in your syllabus. So what is that? Actually, power generating units, that means the generators, right? So in power system, there are different type of generating resources, mainly thermal, hydro, nuclear, and the gas turbine, along with some conventional, non-conventional energies also. So for that reason, but the power generation involves cost, and that cost is recovered from the consumers. So always it should be the aim of any power station operator that power generating unit should operate at economic condition, so that at minimum cost. For hydroelectric power stations, the running cost is only due to its maintenance, because the cost of water is not there, no cost. If there may be any cost, if the dam or reservoir is there, that is reservoir based power plant, then only the running cost will be the interest on depreciation of that initial cost. But for the mainly for the thermal power plant or the coal based power plant, the cost is very high. And this cost is mainly due to the fuel cost, because every time in a huge amount of coal is required, and for that the cost is involved, along with the installation cost, salary, wages of the laborers and the employees, all are there. Still, running cost is more for the thermal power plant. So here mainly in this part of your syllabus I shall discuss about the economic operation of thermal power plant only. But obviously this concept can be extended for the hydroelectric power plant, nuclear power plant, even for the non-conventional power plant also. Because for non-conventional power plant also, it is not that there is no cost issues are there, installations are there. Then otherwise, why we are now still now why we are restricted with the coal-based power plant? We could jump to the thermal or wind, but they have some restrictions, so that may be reflected in the cost. And cost is also depend on the availability also, right? So here, mainly the cost is due to the we shall discuss about the um, thermal power plant, right? So which type of costs are there? There is installation cost, running cost, initial cost for installation, then running cost to run that plant. Now, plant means which is generating power. In a plant, there may be one generator, there may be more than one number of generator. So, plant means which is an area which is generating power. And unit means number of generators in that plant. So plant like is a power station actually. So if there be n number of generators P1, P2, Pi, Pn, then these are each unit of these plants. So this the in figure 1 showing n number a power plant with n number of generators. Here we are assuming all are the thermal power generators. Now, economic operation, how the plants can operate its units economically. Actually, there are two parts of it. One is economic load dispatch and second is unit commitment. What is economic load dispatch? Economic load dispatch is that how the load will be distributed among the generators for a particular at a particular time of a day, because the load is varying from time to time. So at any instant of time for a particular load, how the generators will be loaded. That means what will be the output of the generators, that will be fixed. Ideally, mathematically, if there are n number of generators, we could load them with a loading of P load by n. But that does not happen. That will not run the generator economically. In that case, fuel cost will not be minimum. So what will be the criteria for which the fuel cost will be minimum and all the generators will scatter the load, altogether scatter the load. So all the generator output, summation of all the generator output will be equal to the load, but at the same time the economic criteria should be fulfilled. That means overall cost of operation of the plant will be minimum. So obviously it is every time it will happen. So this is involved with the running cost, not with the installation cost. So in the running cost, the interest depreciation on the installation cost will come. So this is the economic load dispatch. So economic load dispatch is how a load will be distributed among the generators or among the units within a power plant. Now it may happen in this power plant there are m number of generators, right? M number of generators. And among them we are using only n number. So m is more than n. So actually n number of generators are selected from that m number of generators. So how how we shall select? Obviously based on best performance. So that part of selection, that part of study is called unit commitment. That means if there be a set of units in a power plant, if it is not required to operate all the units, then how we will select the unit? That is the part of unit commitment. So economic operation of power generating units actually divided into two parts: unit commitment and economic load dispatch. Here we shall do only the first part, economic load dispatch. Whatever I have told about economic load dispatch or unit commitment, that is written here. Economic load dispatch is also called economic load schedule. It is also called the economic generation schedule. Now, what may be the cost of generation? Firstly, installation cost will be there. That is a huge cost. Secondly, running cost. Now, running cost will have actually two parts. One part is fixed, that does not depend on how much generation is happening. It is required to pay whatever be the generation. That is capital investment cost due to capital investment or interest or depreciation on the installation cost, all those, along with salary, wages or taxes, all those. Now, what is the variable cost? Variable cost is which is the function of generation, which varies with the generation. So that is actually the um, fuel cost mainly, or maybe losses, because if there be more power generation, more power will be sent, so current will be more, so more losses will be there. So, and nobody will pay for the loss. So these are the cost. For economic operation, it is required to optimize or minimize the running cost, which has two parts: fixed cost and the variable cost. Now, variable cost is actually the running cost. Okay, actually the fuel cost. Now, so the running cost of a generator actually has two parts. One is fuel cost, that is required to generate a power, and another is the other fixed cost, salary, wages, tax, all those things. Now, if we plot input-output curve of a thermal power station, then output in y-axis, input in y-axis y. Input should be is independent. Output is actually dependent on input. But actually here we are concerned with about the output. We are concerned about how much power is required. That's why output is in x-axis in case of economic load dispatch problem discussion. So for a particular output of P, about particular generation, how much input is required? That is not actually from the behavior of the turbine, etc. This is not a straight line, but it is a parabola. Now input, that is the British thermal unit on hour or kilocalorie per hour generated, that is actually generated from the fuel cost, fuel. So this input, we can convert this in y-axis, we can convert into fuel scale, how much kg of fuel is required or how much kg of coal is required. And similarly, we can convert them and by multiplied by the cost of fuel or cost of coal to the cost to the fuel cost. So in that way, input-output curve may be converted into fuel cost curve. Why in x-axis rupees per hour? Because generally we estimate the power generation hourly basis. It may be less than that, but generally we calculate hourly basis. We consider load fluctuations on hourly basis. So this is called the fuel cost curve of a thermal generating stations. So it is not a straight line but a parabola. Actually, it is more complex. It is actually nth order polynomial. Here we can represent them as parabola as per our mathematical approximation. Now you see, if Ci is the cost function of ith generating unit with electrical output of the unit is Pi, right? So ith generating unit has the output power Pi. Then we can write that the total cost has three parts: Ci1, Ci2, Ci3. What are they? At first, the first part. For ith generating unit to run that unit, there should be some fixed costs. That may be maintenance, that may be portion of the salary wages to maintain that to that to run that generator. So that part will be fixed. That will not depend on the power generation. Second part, CI2 is the fuel cost part. If you do not understand, you must interrupt me. And if I get disconnected, then you call me. Otherwise, I cannot understand. Then CI2 is the fuel cost that is proportional to power generation, because whatever power will be generated, you will generate based on similar fuel will be required. So fuel cost will be directly proportional to the power generation. The third is cost due to line loss, and line loss is PI. Line loss is proportional to the generation square. Why? Because current is proportional to the power. Actually, S by V is the current. So it is current is proportional to the S, we can write. So S as a part of P, so a current is proportional to P. And actually do not generate any reactive power, we try to generate maximum active power. So we may approximately say that our current will be proportional to P. So current square, loss is proportional to current square. So current square loss will be proportional to the P square. So instead of current, directly we can write cost due to line loss will be proportional to P square. And if we put a proportionality constant, then it will be alpha I Pi square. Now this constant, so this gamma I, beta I, alpha I, all are the proportionality constant, and this will depend on the characteristics of the generator, right? Fixed part maybe depend on that how they have it has been maintained, but the variable part, the proportionality constant will be depend on the characteristics of the generator. So alpha beta will vary from generator to generator. Same 20 megawatt generator, same 20 megawatt generator may have different alpha beta, because their characteristics, their mechanical energy conversion from to electrical energy, the method of mechanical energy conversion to electrical energy will not be same. Two things cannot be identical. So alpha beta will be different. See, this is alpha, cost function is alpha I Pi square, beta I Pi, gamma I. So it is a quadratic cost function. That's why we have represented that one with using a parabola. But actually this is not the quadratic cost function. There are so many other parameters are there. So for that they are actually nth order polynomial, but here we shall consider them only as the quadratic polynomial. Then another thing is required for to get the economic operation of the power of the units in a power plant. That is the incremental fuel cost. First derivative of cost function is with respect to electrical power generation is called incremental fuel cost. So mathematically it is just dCi by dPi or del Ci by del Pi. So actually here we have actually I shall write one more thing. Here I have written del Ci by del Pi because actually del Ci is not only the cost function of the P, but some other factors are there. But here we are only considering it as a function of P, so we can write in this way, right? So actually here as we have represent the cost function as a function of P only, then del Ci by del Pi we can write dCi by dPi. But if there be some other factors, that valve opening, all those, then that power generation, the cost function will be function of those parameters also. Those we have not considered here. That's why the partial derivative symbols are there. Now, what is the dCi by dPi or incremental fuel cost? Obviously, slope of the fuel cost curve, because this is in this cost curve, this is on y-axis fuel cost, in x-axis there is power generation. So this will give you dCi by dPi will give you the slope of the curve. So if you know the slope of the curve, and this is obviously varying from point to point in the fuel cost curve, but at any point if you know the full slope of the curve, then for a particular change in power generation, we can estimate what may be the particular change in cost. There is no need to find out the original cost function. So this is one use of incremental fuel cost. Now, when we try to find out economic criteria, what will be the condition for which the power plants will operate economically, then we have to find out what are the conditions we should maintain when when we want to find out any economic condition. So the first criteria is that power balance equations should be maintained. What is power balance equation? Power balance equation is generation should be equal to load plus loss. In this case, in your part, actually in these third year classes, we shall not consider any loss. So for that reason, if loss is neglected, then generation should be equal to load. So whatever economic generation schedule we find out, this condition should be maintained. All the generation should power summation of all generations must be equal to load. Along with that, every generator has some maximum and minimum generation limit. Minimum generation limit for any generator, ideally it should be 0. But generally we keep it on running condition with some load, because in that case the time required to make it ready for run will not be there. So it can readily accept any loading at any time. That's why generally theoretically P minimum may be 0, but practically we maintain some nominal value of generation, and we do not discard the generation from the system because it takes a lot of time to make it into operation. You have learned that one in your second year classes in power supply system. Similarly, for any generator, there is a maximum generation limit beyond which we cannot generate because it has a capacity. So that whatever economic generation schedule we shall find out, it should have some, it should be within the minimum value and maximum value of that maximum generation limit of a generator. Say for example, a generator maximum generation limit, maximum generation is 20. Minimum generation is 20, sorry, maximum generation is 150. But economic generation schedule is suggesting that 170 should be economical for this generator. But physically, this generator cannot supply the 170 megawatt. So this generation schedule will not be feasible. So some economic generation schedule is suggesting that 110 megawatt generation for this particular generator will be economic. But this will not be possible because its minimum generation is 20 megawatt. Some generation schedule is suggesting that 100 megawatt generation will be sufficient, will be economic for this particular generation. It will be accepted because it is within the maximum minimum limit of the generation. Now, why this generation economic generation schedule will be changed? Depending on load, because if the load is changing, then generation schedule will totally change. It's not it. If the load is increased, then generation will be increased. If the load is decreased, then generation will be decreased. So the economic generation schedule does not mean that is fixed for that generator. That is fixed for the generator for a particular load only. Now let us find out what will be the criteria to maintain economic operation of thermal generating units in a power plant without considering the losses. That means we are not considering any loss, right? Now we know the individual how to represent the individual cost function of a unit. Then total cost function will be summation of all cost. Here I should mention one thing, that you see cost function was Ci equal to alpha pi square beta pi plus gamma I. This is actually the cost function of the generator. But in some, we colloquially say this one as fuel cost function also. Why? Because this middle component actually more dominating. Fuel cost actually the main cost, running cost of any generator in case of thermal power plant. That's why this function or cost curve is also called the fuel cost curve. Now, so what will be the total running cost of this plant? We have to add all the cost of individual generators. Then economic operation is not to minimize individual generator cost. It is to minimize total generation cost of the plant. Then obviously we shall get the best value, best thing. Then with which constant? Equality constant is summation of generation should be equal to load. And inequality constants are also there. That is, every generation must be within minimum and maximum limit of the generation. Now, to find out operation criteria, or we need one optimization technique. So to apply any optimization technique, it needs a constraint equation. If we use the classical method using the Lagrangian function. So what is that? From the equality constraint equation, we derive one equation making the right hand side 0. So we can make summation of Pi minus P load equal to 0, or P load minus summation of Pi equal to 0. We have to make that equation in which variable will come as negative, right? So here variable has come as negative. That's why you have taken P load minus Pi equal to 0. But it is a function, so I have written this function name as a phi, right? Now there is a method, Lagrangian function method, in which actually we derive a function from the cost function, that from the actual function. So actually this was the cost function, this is the constraint function. Using the Lagrangian multiply technique, the method is we shall derive a Lagrangian function which will be the cost function plus lambda multiplying factor, Lagrangian factor multiplier, multiplied by the constraint function, right? Here C is the cost function, because actually this is the objective function that we want to minimize. Here our cost function we want to minimize, that's why it is C. Okay. If we want to minimize transmission line loss, then this C will be the transmission line loss function. That is the method. So in that way, if we write for, in this case, in case of economic load dispatch problem, this is the C plus lambda phi. C plus lambda phi, this is an universal function plus lambda phi, this is a universal method that can be applicable for any minimization technique. Here we are applying this one for cost minimization in case of for economic load dispatch of the from a power plant. Now, if we want to minimize any function, then first derivative of that function should be equal to 0. From there, we shall get that condition. So, if we make first derivative of this function with respect to what? With respect to the power generation, because actually economic generation schedule or economic load schedule will give us actually what will be the generation of each generator, so that total plant can be operated economically. Then obviously we shall take the first derivative of every Lagrangian function with respect to every variable. So what are the variable here? Here variable are the all p's. So all p means p1, p2, pi in this way. So here I have shown for the ith generator. Now when we are taking derivative of lambda function or Lagrangian function with respect to pi, it is actually function of how much? Function of all variables, that is p1, p2 up to n. So we should do the partial derivative, because there are so many variables, n number of variables. So actually this part is in this part only there will be pi will come in the derivative, so it will be minus lambda. And then in C is also function of all variables pi, p1, p2 up to pi. So it is partial derivative of del C by del pi. Now among in the C there are so many costs are there, that is C1, C2, Ci up to Cn, right? So among them only Ci will be the function of pi, others are not. So this partial derivative del C by del pi, we may write dci by del pi. Direct derivative because there is no other variable within the cost function of the ith generator. That's why it is the direct derivative. So in short, dci by dpi will be equal minus lambda will be equal to 0. If you do not understand, you must ask me. Then lambda equal to dci by dpi. Now this is applicable to any number of generators, any generators in that plant. So it is applicable for 1, 2, 3 up to n. So what is in short? Partial first derivative of cost function of each generator with respect to their generator individually will be equal and that is equal to lambda, right? So you see the what is dc1 by dp1? Actually incremental fuel cost of generator 1 or incremental fuel cost of generator 2 in that way. So actually these are the equations we are getting to make the operation economic. So these are the conditions. So how many equations we can get from the equation 5? Can you tell me how many equations we can get from equation 5?
N minus 1.
N number of equations. Because dc1 by dp1 equal to n lambda 1 equation. Similarly, dcn by dpn equal to lambda. So there are n equations, right? Not n minus 1, n.
Okay. Yes, ma'am.
So there we have n number of unknowns, n number of generation we have to find out. But along with that, lambda is also unknown. So actually we have n plus 1 number of unknowns. And here we have n number of equations. So one more equation is required. That is with us because summation of pi, summation of generation equal to load. So that is one more equations. So from here, we shall get n number of equation. From here, one equation. So we can solve all these n plus 1 number of unknowns, right? So we can get one economic generation schedule for that for that plant. Then we have to justify whether that generation schedule is justified, technically viable or not. Because this is a numerical mathematical problem. By solving it, you will get a result, obviously. But whether that result is feasible or not, that we have to check. One thing is that we have to consider the limit of the generation, power generation limit. So if any generation is violating its limit, that means economic operation is suggesting that it should be either be less than minimum value or more than maximum value. But that will not be possible. So in that case, we have to fix that generation to the either in the maximum value or in the minimum value, depending on which side it has crossed the limit. So if say by economic generation schedule, you are getting Pi is less than Pi mean. That is not feasible. So in that case, we have to fix Pi equal to Pi mean. Right? Similarly, for if Pi is more than Pi max, then we have to fix Pi equal to Pi max. In both the cases, when you are violating this, because this is not feasible, we are instead of that you are using this one. That means you are violating this equation. Then what? Then the economic operation will not be there in that case. Then what to do? For the remaining generators, we have to again perform economic load dispatch with the load equal to PL minus PI mean or PI max. Because that generators will no longer be under economic schedule, right? In that way, we have to proceed. Then let us go for some numerical examples. So if the generation limits are not given, then we shall assume that generation limit can be infinity. So we have no need to bother about the what will be the whether it is valued or not. We shall whatever value we shall get, we shall assume that is possible, right? So this example is something like that. Only the cost functions are given, load is given. We have to find out the economic load schedule. So just equate the incremental fuel cost, find out the incremental fuel cost, equate them, and use another equation, summation of generation equal to load. Load is 450. So if we solve it, we are getting 300 and 150 at the generation schedule. And incremental fuel cost, if you check, it will come same, because actually we get this economic generation schedule equating the incremental fuel cost. So it will come same. Sometime along with that, the cost, it is asked to find out cost. So just you put Pi, P1 and P2 in the cost function, you can get what will be the fuel cost, what will be the running cost at that condition. Now there is another example. Say here directly incremental fuel cost is given and load is also given 115 megawatt. It is asked to find out economic load distribution along with what will be the saving in fuel to make this due to this economic distribution instead of equal distribution, right? So economic distribution we can find out by just equating that IFC1 equal to IF2 and P1 P2 equal to P1 plus P2 equal to PL, right? So from there we are getting that economic generation schedule is 50 megawatt and 65 megawatt. Now incremental fuel cost will be same obviously. Now if we want to distribute them equally, equal distribution of load, not economic. Or equal distribution of load, it will be just divided by 2, so 57.5 of each generator. Here we can use that incremental fuel cost, the concept of incremental fuel cost. Incremental fuel cost means slope of the curve is there, okay. Now what is the change in generation? Let me see. So, so incremental fuel cost curve was the slope of the curve. Now here one point we know the generation is 57.5 say. Another point it is 60. We want to know what is change in cost due to this, is not it? Right? So we need del C. We know del P. We know slope of the curve. Now if we just integrate this slope of the curve from P1 to P2, obviously we can get the change in cost. Can you follow me or not?
Yes, ma'am. We can.
Okay. So in that case, what we want to know, due to this equal distribution of load, what is there any saving in fuel, or economic distribution of load, there will be saving in fuel. So we know for economic distribution there will be saving in fuel. So actually from this incremental fuel cost we can get the change in fuel cost. Actually we need change in fuel cost, not in the actual fuel cost, because we want to know the saving in fuel, not in the fuel cost, not the actual fuel cost. So actually this is 57.5 is the equal distribution and 50 is the economic distribution. So if we go from equal distribution to economic distribution, you see there is a negative sign. So there is a saving in fuel, right? Now you see, if for the same case, when we go for the second generator from 57.5 to 65, then cost is dropping, rising, right? So it is 279.375, right? So actual total change in cost is minus 10.125. So there is negative sign, means there is a saving, right? So there will be a saving in fuel. So what will be saving? 10.125 rupees per hour for this particular load from configuration. This negative sign, positive sign may change for the other load configuration, right? So in this way, from the incremental fuel cost, we can know the saving in fuel, because We do not know gamma. Sometimes the determination of gamma, that is constant part of the cost function, is not so easy, and it is not written in the generator, say, what is that called, rate, the actually that label on which the ratings are written in the on the body of generator. In that, the generator alpha beta gamma is not written, because alpha beta gamma is not possible to identify from the generator winding or manufacturing the generator. When it will be in operation, then only it can be estimated. So it is actually estimated from the performance of the generator when it is in operation. So it is not readily available from the rate card of the generator, where it is the rating is written. Some name is there. I forgot. Cannot remember right now. Now another example is there are three generators. Since you have to do it manually, so in your case only up to 3 generator case will come. So if there are 3 generators, here the fuel cost curves are given. Instead of that, IFC may also be given, that incremental fuel cost. And the generator ratings are given. That means maximum generation possible is this much. Minimum value is not given, then we shall assume that minimum value 0 megawatt is there, 0 is there. Now we have to distribute 25 megawatt load among them economically. Now it is, if we find out using incremental, using that equating the incremental fuel cost, I have not shown here because you can do it by yourself, then you can get this one. So PG equal to 48 less than 75 megawatt, PG1 is 76 less than this 100, but PG3 is 126, but its rating is 120, right? So it is beyond the limit. It is not possible. Then we have to fix the PG to the 120 value, right? So 120 value means this much. So if when PG is 120, then remaining load, obviously when PG is 120, then remaining load will be the 130. That should be distributed among the remaining generator. That means generator 1 and 2. Using again these two cost curve, we have to distribute the load 130, right? So in this way, we have to proceed. Here you have seen that with the 130 megawatt load distribution, the PG1 is 50, PG2 is 80. So it is feasible. But if it would come, because what value will come, that will depend on the cost function. If it would come 80 and 50, just opposite, then it would not be possible. Because for generator 1, the maximum generation capacity is the 75. Then we have to fix it to 75, and the remaining 55 will be catered by the generator 2. And in that case, economic generation of the plant would not be possible. But the generation is possible, but economic generation will not be possible. Then in that case, running cost will be more. It should not be economic. So economic general load dispatch problem solving, it does not mean you just equate the IFC and find out the solution. After finding out the solution, we have to check whether this generation schedule is feasible or not. If it is feasible, then it is all right. If it is not feasible, then we have to find out the feasible generation schedule. And we try to maintain economic generation schedule as much as possible. That's all for today. Next class, I shall start the compensation, right? So that's all for today. You write your name and roll number in the chat box.